Hi, I am Jashwita Ravla and my teammate is Alan. We are going to present a paper on cloud detection using abstract syntax tree. It was written by Baxter, Andrew, Landro, Anna and Lauren. Let's get started with authors and journal. Baxter has H-index of 17, Landro has H-index of 43, Anna has H-index of 24. I did not found the other two authors' H-index. This paper was published in International Conference on Software Maintenance in Maryland. This paper was cited in 176 by articles. Here are some research questions like how to remove clones from the program, how do clones form. So this is the primary motivation of the paper because they found limitation of previous cloud detection is limited either exact textual match or nearly miss only for a complete function bodies. So they are using now abstract syntax tree for detecting exact and near miss clones for arbitrary fragments of the source code. Before going to further, let me introduce to the basic. Clone is a program fragment that is identical to other fragments, and nearly missed clone is a fragment which is nearly identical to others. This nearly missed clones occur when the clone is copied and then edited, which gives rise to nearly missed clones. They generally occur due to copy paste. Now let's get started with the how do clouds form. So in a software design or it has structured design and formal reuse methods. A particular amount of code is produced by ADHOD reuse of existing code. So developers, if they want to implement new functionalities, they find the code which is familiar to that and then copy paste and then modify that code. The author gave an example of it about device drivers, which device drivers for operating system most of the code is boilerplate and only few drivers from the hardware have to change. Then we copy code from the trustworthy drivers and copy to new drivers, which is a good practice of code reuse and it consists of bugs. Sometimes a style of coding or regularly needed code fragments will arise, such as error reporting or UI display. The fragment will be purposely copied to maintain the style, so the fragment contain more knowledge of some program. Sometimes programmer does not need to copy due to conscious memory. They can repeat the code for the definition. So sometimes they write same code again and again scattered in different places, so it will cause clones. Instead they can use library functions, which is good. Sometimes clouds exist due to performance reasons in tight time constraint system and in accidental alone case. Now we are going to detect clouds using ISTS. Finding clown is difficult. We can find through cloud fragments, but still we have to divide the code into fragments and should check which will halt and give some results, which is practically impossible. So they did deep semantic analysis to find out equation detection. Semantic design, they built a transforming modify large software. First they parse source code with ASTs and then apply three algorithms, namely first one detecting subclone algorithm, sequence detection algorithm, and detecting near-miss clones. So let's get started with finding subtree clones. In finding subtree clones is easy, but in practice several problems arise like subclone problem, near-miss clone problem, and scaling problem. In subclone problem means we wish to recognize maximally large clones, so like clones, subtrees need to be removed or reported as a clones. Next one is scaling problem, which takes large amount of computation time. To tackle this issue, they partition the set of comparison by categorizing subtrees which has values. From this we can find exact subtree clone. For example, for a bucket B, if we use hash tree, then we will compare the tree in the bucket B, so it decreases the computation time, but it is only applied to the exact clowns. If we apply to near miss clowns, it doesn't work because they introduce bad hashing things which ignore small subtrees. Instead of comparing trees for exact equality, they found simplicity. Through simplicity, how similar two subtrees are. This is the simplicity formula. From this, they'll calculate the mass threshold parameter specifies the minimum subtree mass to be considered, so that small piece of code will be ignored. This is the basic subtree clone detection algorithm. Here you can see that in step 2, they will apply hash code and place into respective buckets by ignoring small subtrees. After that, every pair of subtree located in same hash bucket is compared. So similar is calculated and added to clown list and clowns are removed. From here, Ellen will continue. Thank you.
My name's Alan. I'll be presenting the second half of this paper. So previous examples were based purely on syntax when sequences of clones are more interesting. These sequences appear as a right or left-leaning tree as shown in figure 2. These sequences are then looked at with other misses and near misses. By visiting the parents of the clones, they're able to ensure that no near miss clones are skipped. Finally, instances of the same clone are grouped to show the frequency in which a clone occurs. Now we'll look at some of the issues in building a clone detector. So each language has a specific dialect. Not just that, but each program or application can also have its own. Subtle nuances which are particular to that specific application developed by a specific company. It's necessary to be able to parse the information accurately. Sometimes a custom parse will be required. Related to language, computer-specific such as preprocessor directives must also be carefully inspected. Preprocessor directives such as the #include statements in C++ can be cloned just like any other portion of the code. For this reason, they must be looked at. However, they don't follow the same formatting as the rest of the language and must be looked at differently. Several methods exist to solve this, such as adding them to the language syntax, essentially making them an extension of the language, or running the preprocessor to remove any unstructured directives. Any clones that are found in this stage must be marked as part of the include file, not the including file. Scaling is another issue which must be addressed. There's only so much RAM and or disk space able to store the trees, comments, and other important information. When working with very large source codes, the design must be careful to use only the amount of storage necessary. Alternatively, the program can be changed from a batch compute to an incremental computation, which results in less memory being used at any given time. Improved language parsing algorithms would allow for higher accuracy and a quicker detection of clones. Additionally, being able to find two segments which were clones but have been patched differently. This can be useful as it will show where an identical piece of code was changed in only one location. This is likely a bug which was patched in one place but left in another. Another challenge is finding a representation in which the data flows are explicit. This would allow for a more semantic-oriented detector. Finally, with knowing all about clone detection, we can discuss future work involving what we learned from this paper. The ability to automatically remove detected clones, or to have detection processes placed within a software engineering check-in would be beneficial. This would allow them to be found quickly and more efficiently, saving both time and money for the company. Additionally, both improving the efficiency and memory footprint of the application would be necessary for larger source codes. Currently, 600 megabytes of RAM and 122 minutes of CPU time is used for 100,000 source lines of code. While these numbers may seem small, it's important to remember this study was done in 1998, where the average amount of RAM in a computer was 64 megabytes. However, it's also important to know that while we may have more RAM nowadays, source code, instead of being in the hundreds of thousands, is now in the millions, if not tens of millions, meaning improving the memory footprint would still be a necessary challenge to overcome. Finally, changing the detection method from thresholding will allow the detector to be able to detect near miss clones and small trees. Hope you enjoyed learning about clone detection.